Gases are wild, aren't they? I mean, they expand, they compress, and they literally power everything from everyday car engines to massive hot air balloons. Welcome to another edition of The Explainer. If you're a grade 11 chemistry student looking for a serious advantage on your upcoming exams, well, you are in the exact right place. Today, we're setting out to completely demystify the physical states of matter and the seemingly complex math behind how gases actually behave. We're going to take the formulas, the theories, and all those calculations and just break them down, step by step.
So let's take a quick look at our roadmap for today. We're going to cover the four states of matter, kinetic theory and motion, Boyle's law, Charles' law, Gay-Lussac, and molar volume, and finally, we'll bring it all together with the ideal gas equation. Let's dive in.
Section 1. The four states of matter.
All right, so everything around us is matter. By definition, matter is simply anything that occupies space and has mass. Traditionally, we think of it existing in three really common states, right? Solid, liquid, and gas. Think about water for a second. You've got ice as the solid, everyday water as the liquid, and steam, or water vapor, as the gas. Now, an absolutely great way to categorize these for your exam is to remember that solids and liquids are called condensed states because they have much higher densities. Liquids and gases, on the other hand, they're known as fluids because their particles are totally free to flow around.
Let's look a bit closer at those condensed states. Contrasting liquid water with solid ice is a brilliant way to see why solids simply cannot be compressed. In ice, those hydrogen bonds lock the molecules into this incredibly rigid, highly organized hexagonal crystal lattice structure. There is literally no wiggle room. In a solid, the particles, whether we're talking atoms, ions, or molecules, they only vibrate in fixed place. They don't shift around.
Now, by messing with temperature and pressure, we trigger phase changes. You know, melting solids or turning liquids into gas through evaporation and boiling. But check this out. There is actually a fourth physical state of matter, plasma. Plasma exists at extremely high temperatures. We're talking millions of degrees Celsius. Under these absolutely intense conditions, molecules can't even hold together. Atoms are literally stripped of their electrons, creating this highly energized, gaseous soup of positive ions and free electrons. It's essentially an ionized gas.
Section 2. Kinetic theory in motion.
So, moving to the microscopic level, the kinetic theory of matter gives us three foundational rules. First up, every single substance is made of tiny particles that are in continuous, random motion. Second, all these particles possess kinetic energy, which is the energy of movement, as well as potential energy. And third, the amount of that energy dictates the phase of the matter itself. Molecules in a solid have the least amount of energy, while gas particles, they've got the most. Because they move so incredibly fast and randomly, gases diffuse very quickly. This is actually known as Graham's law, and it's the exact reason why you can smell someone's overly strong perfume from all the way across the room almost instantly. That high-energy state of gases is the foundation for literally everything we're about to calculate.
Section 3. Boyle's law. Pressure and volume.
Okay, so the first truly reliable measurements of gas properties were made by an Anglo-Irish scientist named Robert Boyle, way back in 1662. Boyle discovered a very specific relationship between pressure and volume. His law states that for a fixed mass of gas, the volume is inversely proportional to the pressure, as long as the temperature stays completely constant. The mathematical formula you absolutely need to memorize is P1 times V1 equals P2 times V2. Just think about plugging the end of a medical syringe with your thumb and pushing the plunger down. As you decrease that volume, the pressure pushing back against your thumb skyrockets. You can actually visualize this math happening in real time. Imagine a cylinder with a movable piston inside it. At 1 atmosphere of pressure, the gas has plenty of volume. But as that piston pushes down, doubling the pressure to 2 atmospheres, the volume shrinks by exactly half. If you ramp the pressure up to 4 atmospheres, the volume drops to a quarter. Pressure goes up, volume goes down. It is a perfect inverse relationship. Now, when you graph Boyle's law, putting volume on the y-axis and pressure on the x-axis, it creates a hyperbolic curve that plunges down sharply and then levels out. I want to point out a huge, very common exam mistake right here. Students often try to just draw a straight downward sloping line. Please, do not do this. Because the relationship is inversely proportional, it has to curve. Recognizing that specific curve is basically free points on your test.
All right, let's put this into practice. I want you to pause the explainer on a second and try solving a real-world problem. Sulfur dioxide, which is a gas found in vehicle exhaust that forms acid rain, is sitting inside a 1.5-liter sample at a pressure of 5.6 kilopascals. If that pressure is cranked up to 15.0 kilopascals while the temperature stays exactly the same, what's the new volume of the gas? Go ahead and give it a try.
Okay, how'd you do? Let's walk through it methodically together. Step 1. Identify what you already know. Initial volume, V1, is 1.5 liters. Initial pressure, P1, is 5.6 kilopascals. The new pressure, P2, is 15.0 kilopascals. Step 2. Set up Boyle's equation. P1 times V1 equals P2 times V2. Step 3. Rearrange it using some basic algebra to isolate V2. So, V2 equals P1 times V1 divided by P2. Multiply 5.6 by 1.5, then divide that result by 15. You should find that the new volume decreases down to 0.56 liters.
Section 4. Charles' Law. Temperature and volume. Fun fact here, in 1787, a French physicist named Jacques Charles made the first ever hydrogen balloon flight. It was actually so terrifying to the local villagers that they attacked his balloon with pitchforks the second it landed.
Because Charles worked a lot with balloons, he was super interested in how heat changes gas volume. He discovered that the volume of a fixed mass of gas at a constant pressure varies directly with its temperature. Simply put, if you heat a gas, it expands. If you cool it down, it shrinks. The formula to represent this is V1 over T1 equals V2 over T2.
Now, here's an insider tip that is definitely going to save you some points. It is absolutely crucial to keep these first two laws straight in your head. Boyle's law is an inverse relationship between pressure and volume. One goes up, the other goes down, and temperature is the constant. Charles' law is a direct relationship between volume and temperature. They both go up or down together, and pressure is the constant. Mixing up which variable is held constant is honestly the #1 reason students lose marks on gas law exam. Time for another quick pause and think. A sample of gas at 15 degrees Celsius and 1 atmosphere of pressure has a volume of 2.58 liters. What volume will it occupy at 38 degrees Celsius at that exact same 1 atmosphere of pressure? Pause the explainer and set up your formula. But wait, before you do, let me warn you about the absolute biggest trap in all of gas chemistry. Temperature must always be converted to Kelvin. You have to add 273 to your Celsius temperatures before you do any division, where your answer is going to be totally wrong.
Section 5. Gay-Lussac and molar volume.
Let's talk about Joseph Louis Gay-Lussac. He was a French scientist who basically asked, what happens if the volume is held strictly constant, like if the gas is trapped in a rigid sealed steel tank? Well, he proved that at a constant volume, the pressure of a fixed amount of gas varies directly with its temperature. If you heat the gas, the particles fly around much faster, they smash into the walls harder, and that drives the pressure up. The formula for this one is P1 over T1 equals P2 over T2. Now, to get the full picture, we also need to factor in the actual amount of the gas itself, which brings us right to Avogadro's concept. He showed that if you have two samples of gas sitting at the exact same temperature and pressure, their volume is dictated purely by the amount of the gas, the number of moles. The formula here is V1 over N1 equals V2 over N2, where N stands for the number of moles. Makes sense, right? If you pump in more gas particles, the volume has to increase.
And this leads us to a magic number that you absolutely must memorize for your chemistry journey, 22.4. The volume occupied by exactly 1 mole of any ideal gas at standard temperature and pressure, or STP, is standard molar volume, and it is practically constant across all gases. So lock this in. 1 mole of an ideal gas at STP takes up exactly 22.4 liters of space, no exceptions.
Section 6. The ideal gas equation.
Everything we've studied today builds up to this one grand finale. First, if we merge Boyle's, Charles, and Gay-Lussac's rules together, we get the combined gas law, which is just a single equation that lets us track pressure, volume, and temperature changes all at once. But when we add Avogadro's moles into the mix, that culminates in the ultimate equation, the ideal gas equation. This single framework allows us to calculate any missing variable of a hypothetical ideal gas. An ideal gas is basically a gas that perfectly, flawlessly obeys all the mathematical rules we just discussed without any messy intermolecular forces getting in the way.
But I want to leave you with one final provocative thought. The ideal gas equation describes a perfectly hypothetical ideal state. In the real world, real gases only actually obey these laws closely when they are at very high temperatures and very low pressures. So, why do you think that is? What happens to the physical volume of the gas particles themselves, or those tiny, tiny attractive forces between them when a real gas is super compressed and cooled way down? Think about the constraints of reality versus a perfect mathematical theory. Keep that question in the back of your mind as you head into your next chemistry study session. Thanks so much for hanging out with me on this explainer, and good luck mastering those exam calculations. You've got this.